Hi, my name's Alyssa North. I'm a professor of landscape architecture at the Daniels Faculty of Architecture, Landscape and Design at the University of Toronto. I want to welcome everybody to the Sky Analytics live demonstration with Jamie Reford, CEO of Sky Analytics, and his colleague, Adrian Kudzma. Thank you for joining us today. Before we begin, I wish to acknowledge this land on which the University of Toronto operates. For thousands of years, it has been the traditional land of the Huron, Wendat, Seneca, and the Mississaugas of the Credit. Today, this meeting place is still the home to many Indigenous people from across Turtle Island, and we are grateful to have the opportunity to work on this land. Daniels honors Indigenous peoples, past, present, and future, here and around the world, and we wish to pay respect to local elders, including those of the lands from which you are joining us virtually today. Sky Analytics Inc., Jamie Reford, launched Sky Analytics Inc. after graduating from the U of T Daniels MLA program in 2019. Leveraging the accelerating data capture potential of UAVs and associated payloads, Jamie and the Sky Analytics team are focused on optimizing the resilience, efficiency, and value of digital design tools through the integration of scalable UAV, AV spatial data capture, processing, and output workflows. And they will be explaining all these things to you today. Adrian Kudzma is partner at Sky Analytics Inc. and co-founder of Altitude Geospatial Inc. Adrian has over a decade of experience working with global leaders in LiDAR space. He has traveled around the world in his capacity, helping clients streamline their LiDAR collection and processing workflows. Adrian now works predominantly with UAV LiDAR platforms, seeing this as the future of detailed mapping applications. Please note that this is being live streamed and recorded. If you do not wish to be captured, please turn off your video. We ask you keep yourself muted throughout the presentation. You may add your questions in the chat for me to relay to Jamie and Adrian, or if you wish to ask your questions directly, please put your name in the chat and a note that you wish to ask your question on camera. Now allow me to welcome Jamie Reford.
Hi, Alyssa, thank you very much for the intro. Looking forward to sharing this data set that we captured of the U of T building, 1 Spadina Crescent. I will proceed today. We've got a brief presentation, and following that, there'll be a short video that we put together just demonstrating the process that we use to capture the data. I'll then hand it over to Adrian, and he will demo the data set, and we can kind of walk through collectively what the outputs are being demonstrated on the screen and the various applications for urban planning, landscape architecture, civil engineering, etc. I'm just going to go ahead and share my screen to get the presentation started. Maybe Alyssa, if you can give me the thumbs up if you can see what I'm seeing here. Okay, we all set? Perfect. Okay, so as mentioned, we thought it would be a valuable experience to use the Daniels architecture building as the point of focus for this case study. Easy to communicate, a very compelling space. So you will see that featured throughout this presentation. This is us, Jamie Reford, Adrian Kudzma. Our colleague John Henderson could not be with us today. He's actually on a job in Nepal. As mentioned, our main focus really is to optimize the resilience, efficiency, and value of digital design tools through the integration of drone data capture. Some of the traditional challenges facing spatial data right now, first and foremost, cost. It can be very expensive to capture high resolution geospatial data. Resolutions themselves vary widely depending on how the data is captured. If you're using ground-based systems, very accurate, very expensive. Satellite systems and traditional aircraft, slightly less expensive, but much less accurate. And then finally, the standardization of this data process is not uniform depending on the applications. These are all issues that we are looking to solve through kind of the integration of drone data sets. Ultimately, kind of the two pillars informing why we believe that UAV data is so powerful. First of all, better data for informed decisions. There are incredible now design tools for infrastructure and urban development planning and project implementation out there. But the data sets used to inform these projects ultimately determine the quality of the outputs. So good data equals informed decisions, and then cost efficiency as well. These are some of the tools that we're using on a fairly consistent basis. Enterprise UAV fleet, that's a DJI Matrice 300 drone equipped with a SureStar Genius LiDAR platform and a GNSS system in the background to georeference all of the point cloud data. And we'll get into a little bit more detail regarding the process behind that in a bit. Some of the standard outputs that we generate for this data set, it was LiDAR and optical data overlaid to create a uniform data set. If you're not familiar with LiDAR, no problem. I'll cover that very briefly in the next few slides here. But essentially we're using a LiDAR payload mounted on a drone as well as on a vehicle to collect in a mobile capacity extensive swaths of terrain and building data. This graphic here at a very high level illustrates kind of the aerial LiDAR data capture process. Adrian will get into the specifics of LiDAR as we demo the data set itself, but essentially we are flying back and forth over a target area. It can be terrain, it can be buildings, it can be infrastructure. And that LiDAR unit is mounted to the drone. In this diagram, it's depicting an aircraft, but ultimately it is sending laser pulses back and forth between the unit and the ground, and those returns are then registered as points with an X, a Y, and a Z coordinate. And the various outputs range from DSM files to terrain modeling to canopy cover. But again, we'll address this in a bit more detail. Optical data sets, obviously, this is a very standard use case for drones. This is the predominant use case, I would say, in the industry thus far. You can generate 2D and 3D outputs using photogrammetric software. But the focus of this webinar is LiDAR. If there are any questions pertaining to photogrammetry or other sort of optical or thermal, feel free to reach out offline and we'd be happy to discuss. Obviously, positioning this data on the Earth is incredibly important. Otherwise, it's frankly useless. So, combining telemetry with the IMU of the drone itself is how we collect the data set itself. Is Adrian here just setting up the base station to establish satellite position GNSS lock for the LiDAR unit. And then in terms of our workflow, this will be covered very shortly in the video that we'll kind of walk through detailing our process. But we essentially go out, we conduct a drone flight, quality control all of the raw data on site to make sure that all of the initial inputs and parameters meet spec. Way easier to recollect on site if you notice an anomaly as opposed to identifying something once you're back at the office. Assuming all the data checks out, run initial processing, and then we can run additional machine learning macros and AI macros to classify and further scrub the data as required. And then the outputs, again, depending on what is spec'd, these outputs are compatible with all standard off-the-shelf softwares produce by Autodesk, Bentley, Rhino, Esri, as well as gaming engines are now becoming increasingly involved in the infrastructure urban development design space. So Unreal Engine and Cesium both now have plugins available to ingest this raw data as well. And then before we jump into the video here, I mean, we cannot stress this enough. Drones are fantastic tools, but ultimately they are tools and not toys. You're sharing airspace with planes and helicopters, and the regulations in most areas around the world now consider drones as a type of aircraft. So making sure you're operating safely is critical. Obviously, complying with all the regulations in whatever jurisdiction you're operating, also critical. And then mission planning, depending on the kind of data sets that you're looking to capture, really understanding the desired outputs before you conduct your mission will save you a ton of time in processing after the fact. So being very diligent with your mission planning, making sure you're collecting and covering the optimal areas and setting the resolutions to what you'll need, before you actually go out and fly is very, very important. And just to build on that, this is, a kind of our standard high-level flight planning process here. We'll just use Google Earth or a standard off-the-shelf software tool, but there are various elements to consider, especially in an urban context. So you can see in the middle of the screen here in orange, this was the flight plan that we ultimately flew. We're marking additional obstacles to avoid. We've got a school and an active building site with a crane marked in red, and then a CAMH facility marked in green. So these are all things that you want to be considering prior to flying. Now, we'll actually get into the operational stuff here in a minute, which is, I would say, much more interesting. Okay, so we'll just play the video. So this is the site itself. Daniel's building is a fantastic facility. I went to school here, so I'm slightly biased. But we set up in the back of the building, making sure that we had line of sight at all times while the drone would be in the air. So this was the most open spot. While we're setting up, being very cognizant of the fact that this is a public space. We had the permission of the property owner, obviously, to conduct this data set, but we still want to mark out and clearly delineate our operational area so that people do not walk through. Entering into the actual flight control component of the drone, there are several different parameters, and again, this will change depending on the type of drone that you're flying, but you want to make sure that you conduct a thorough checklist prior to every operation. Make sure that your maximum altitude is set appropriately, maximum flight distance, all your firmware is updated and whatnot. So this is, a standard process for us. We spend minimum 10-15 minutes before every flight, just making sure that all the flight input parameters are set correctly. It's a requirement as specified in the regulations. It'll save you, a ton of time operationally and from a safety perspective as well. It's critical. These drones, especially the enterprise drones, now have fantastic software inbuilt to add levels of safety. But if you're not verifying that your parameters and inputs are appropriate to your operational context, then all that technology is for naught. We can get into a bit more detail if there are any further questions with regards to kind of operational inputs. Feel free to reach out offline or ask in the Q&A session as well. But here we're just going through looking at the battery warnings. LiPo batteries are used for the drones that we're flying. In this case, we're in controlled airspace, so it will ask you to accept responsibility for the flight. We had obtained prior approval from NAV Canada to access the airspace. So now we're up in the air. That's the LiDAR unit payload attached to the bottom of the drone. Now operating, moving to the initial flight plan. This is in manual operation currently. Once the flight plan is uploaded, as you can see on the screen now, the drone is actually flying itself based on the input parameters. This is the view from the first person view camera on the unit itself. You can see we're marking various important elements here: flight speed, altitude, the two blue icons you can see in the top screen. That's actually marking active aircraft in the relative airspace. So obviously keeping tabs on airspace activity is critical. This is sped up here. The mission itself took, I believe it was just over 18 minutes to fly from takeoff to touchdown. And the resulting data set here, this is purely aerial LiDAR data set captured on this initial mission. We also disconnected the LiDAR unit from the drone and then mounted it to a vehicle to supplement the aerial data with ground-based mobile data as well. So, the resulting data set that we'll be demoing shortly is much more rich and detailed as a result of that fact. Again, just takedown process, making sure you're incredibly organized here, making sure that the site area is still blocked off. And now we're viewing the LiDAR unit as mounted on the vehicle. So it's performing exactly the same function as it was on the drone. Inertial measurement units are being taken. It's still relaying data to that base station that was depicted earlier in the slide deck. And these two data sets, they will be logged as separate files, and then we merge them in post-processing to relay or to compile the final data set. I'll just quickly share here, an operational document that I think is, relevant for all operators. It's important to note, you need to be certified as a drone operator in Canada, and you need to conduct something called a site survey every time you fly. So if you are thinking of implementing drone operations into your future workflow, this type of documentation is critical. So you can see here, we've got mission overview, flight plan, the name of the drone, pilot certificate number, lat/lon. And then just reminders, we were flying near Billy Bishop, as well as the two heliports at Toronto St. Michael's and Hospital for Sick Children. So this document contains all relevant information pertaining to those aerodromes. So I'll hand it over to Adrian now, and he can actually preview the data set, and he'll run through the various applications, and then we'll open it up for a Q&A.
Thanks, Jamie. Just going to share my screen with everybody so that you can see the data. So first, I'd like to take a step back and sort of mention some information about the equipment that we use. So when we use LiDAR data, it's comprised of a few items that give us the final point cloud result. We have our GNSS unit inside the equipment, inside the LiDAR equipment. We have our IMU, inertial measurement unit in the equipment, and we have our laser. So what we do is we combine those three pieces of information to produce an accurate point cloud that is georeferenced. The GNSS gives us our X, Y, and Z positioning information. The IMU gives us our roll, pitch, and heading information. And then the point cloud, the laser gives us our measurement to the ground, and basically our features that we're gonna be outputting later on in the process. So when the data is being collected, we have the three different subsets of the system recording this data separately, and then it's combined in post-processing to produce the point cloud. The final point cloud is usually outputted in LAS format, which is industry standard for point clouds. And from that point on, this data can be used and manipulated, analyzed in any way possible so that you can pull out the information that you need from the point cloud. Not sure, Jamie, is this the point cloud data that you guys see on the screen right now? I'm not sure if I'm sharing the correct screen.
Jamie, you gotta unmute.
I'm seeing the DSM at the moment.
Oh, sorry.
Oh, good.
Okay. All right. So here is this is I'll go step by step. So this is the mobile scan that we did of the area. So as you saw on the end of the video there, we mounted the LiDAR unit onto the car and did a couple of loops around the building to pick up some the side features of the building that aren't that well detected when you're flying over top of buildings, for example, from the air. So if we zoom in, as you can see, none of the areas have their roofs, but what we can see is if we zoom in, we can clearly see that the building edges are very well defined and picked up by the point cloud. So this is just a raw output of the building, of the Daniels building from the mobile scan. The coloring just represents how the elevation, so the lower you go, the color is blue, the higher you go, the color is red. So we can see basically from ground level what the laser saw is what the laser picked up for us. Now, if we add to this data set the UAV data collected, you see that it picks up all of the roofs and adds extra detail to the point cloud that was collected. So you can see more detail on the rooftop and the surrounding areas, surrounding features of the data that was collected in the building. Now, from this point, so this data, now that it has been calibrated, what I mean by calibrated is matched line to line, georeferenced properly and everything. What we do is we can generate some other outputs from these data sets. Usually people are interested in extracting certain features, identifying points in the data, getting elevations, like Jamie mentioned, digital terrain models, digital surface models, and we can extract that using algorithms, like Jamie mentioned, the AI, classifying some of the data in different ways. So I'll jump over and share my screen and software now. So here we have the same data set. Basically, I'll just color it by elevation, show everybody. So this is pretty much the same view that we had in the previous data set that I showed you, looking at the building from the top, but this is now just colored by elevation. So what now from this point is we use the software to classify out certain features. So I ran some classification on this data set and just extracted a few different features. So the different colors represent vegetation. The red is the building structures, and the orange, brownish orange is the ground. So if somebody is interested in, for example, just the buildings, can remove all of the vegetation features, and we have the building and the ground data located there for you. Vice versa, if somebody just is looking for the vegetation and wants buildings removed, for example, buildings, you have that option as well. You can do your analysis of that, and the last feature that you can do is just have the bare earth from all those features removed. Now, another option, what we can do is we can apply RGB point to the point cloud. So from the camera imagery, we can apply RGB coloring to the point cloud, which creates a very interesting data set that you can visually appealing, which is basically a point cloud colored by the RGB information from the pictures, which you see you can still, it's still a point cloud that's collected, but it's just the features are now colored by the RGB information from the camera. Certain different ways that we can show this this data is by flying directly in LiDAR facing camera, which is just straight down. But if you want to get the best kind of detail on the sides of the buildings, you would fly sort of an oblique looking camera, which then gets most accurate coloring on the side of the walls of the buildings, etc. From this point on, what we can also do is go and remove all the features from the point cloud and create a bare earth model, which can be used for many different applications. And we can see that this is without any buildings. This is the features that we have on the ground, and what the surrounding areas look like. From that point, moving forward, you can generate your contour lines, you know, water flow lines, where, for example, if we increase the water levels, where the water is going to be sitting most of the time. Many different applications that I'm going to mention in a few minutes that we can use this data for. So that's pretty much the data set that I wanted to show everyone. Now the next step is certainly different applications that we can use this data for. So some of the applications that we use the LiDAR data for includes civil engineering. So that includes things like mapping to help with leveling of the terrain. So that's creating a digital surface model, or sorry, digital terrain model to show, for example, water runoff, things like that. Planning and infrastructure operation, risk mitigation on, for example, construction sites, or you know, when putting up power lines, things of that nature. Asset management, cleaning up efforts and management after a natural disaster occurs. We did a survey like that last year in Asia after the tsunami, where we mapped out a city that was hit by the tsunami for the cleanup efforts. So there's a few different applications there. Another big application in Asia, South America, even here in Canada, is forestry. So you want to manage, so we would fly a survey over the forested areas to map the forest and optimize the management of tree resources, to monitor growth, detect changes in the forest, see where, you know, where we're cutting down trees over time, see how that area is expanding, and then detecting, you know, the growth, new growth in those areas. Another application is, which is also pretty big, is corridor mapping. So power line survey to detect the sag of the power lines. The more sag you have in the power lines, the less efficiently the energy travels. So power hydro companies are very interested in this type of data, as well as vegetation encroachment on power lines. You don't want trees to grow really closely because of a storm, could rip down the power lines. Least cost paths for new construction. So if let's say we want to build somewhere, what's the best route from point A to point B to build a power line or a pipeline? And also we can use it for railway applications. Mining is another great application, which gives us the, once we have the data collected, we can extract surface and volume calculations to optimize mine operations. We can also get data to plan out future mine extensions. We can also assess environmental risks to see where how it's going to impact the surrounding areas or cities or towns around the mine. Disaster management is another big one, like I mentioned, the flood mapping or even updating flood maps, because the current flood maps for majority of the cities around the world is really outdated and the resolution isn't really accurate, isn't really that detailed. So there's a lot of floods going on, and people, insurance companies, are really interested in this kind of information. Mudslide mapping, change detection, for example, erosion, like we did a survey in the bluffs, just to, and we're going to do it over a while just to see how quickly that area is eroding. And the last one that I sort of always like to throw in there is LiDAR is really well used in archaeology, because we can fly, as you know, LiDAR can penetrate through the canopy of the forest, through the canopy of the trees. So it's good for archaeology because we can map what's underneath the forest, which gives us, quicker turnaround times to eventually head out to these areas and to start pinpointing areas that we're interested in where there could be potential archaeological discoveries. Once you have this data and you have your specific application determined, there are a few different output formats that the data can be submitted to the end user in. Standard, what comes out from any LiDAR equipment is LAS format. Any manufacturer produces LAS files, LAS or LAZ, which is a compressed format of the LAS file, and also a text file, which is just an XYZ file containing the coordinates and elevation of the points that's being collected. Once you have that data, there's many different formats that we can output the data in, including DWG for CAD, for Autodesk CAD, DGN files for Bentley MicroStation use. From there, we have vector data, which is the point cloud. We have raster data, which is the imagery data collected from the air, from the flight. So all that information is available after the data is collected of your area of interest, which was our building area, which was our Daniels building area that we did from the U of T site. I'll pass it over to Jamie. That was mainly the few things that I wanted to discuss at this point.
Yeah, for sure. Thanks, Adrian. So, I mean, that essentially concludes the demo in terms of the data set and the process. Happy to field any questions from viewers or or anyone else that might be interested. We'll make this data available as well, either through the Daniels or via our website directly or via the U of T map and data library, and we'll keep everyone posted on where it's going to live. And then, just if there are any other questions regarding, operational details with regards to drones or LiDAR, as the case may be, please don't hesitate to reach out. We'd be happy to answer.
I might just sort of kick things off by asking a question. I'm curious to know, particularly for, say, landscape architecture applications, how would you sort of consider the difference or the accuracy difference between, say, a survey that you might get for topographical information and for, tree locations, maybe even like DBH of trees and so forth. How does that sort of accuracy compare in terms of what you might be collecting through LiDAR versus a surveyor?
Yeah, that's a great question. And ultimately, it depends on the hardware that you're flying. So for this particular demo, we're flying SureStar Genius LiDAR, mapping grade sensor. The main distinctions are mapping grade and survey grade. The difference in that context is essentially you're dealing with data that's within 2 to 5 centimeters absolute accuracy versus sub-millimeter accuracy for a survey grade system. But for landscape architecture applications where as you're mentioning, you're looking for detailed topographic information, or tree locations, or DBH tree drip lines, whatnot, we have the capacity in post-processing to essentially segment out each individual tree from a forest canopy, and tag each tree digitally as is kind of required. But I'll let Adrian kind of follow up on that.
Yeah, so as Jamie mentioned, the accuracy depends on the equipment, and also the GPS conditions on that day. That GPS, as you know, it depends. GPS is a main contributor to where those points are placed on the ground. So you could imagine if the GPS conditions are bad and we're getting, for example, 20 centimeter XY accuracy, we're not going to get data that's less than 20 centimeters accurate. UAV LiDAR technology has advanced really rapidly over the years, and now with the Genius system, with the combined GPS error and laser measurement errors, we're around less than 10 centimeter accuracy. For every point that is sprayed on the ground. And I guess another big difference between the traditional survey and the LiDAR point clouds is the amount of detail and the amount of information that you're getting. Over that Daniel's building, we got over 100 points per meter, where in a traditional survey you're doing, depends how you stake out the area, but you're doing every probably few meters or tens of meters a point if you're lucky. Right.
Are you guys, would you be able to give like a cost comparison on that? Like, is it cost effective to go this route?
Yeah, go ahead.
Absolutely. I mean, again, it really depends on your use case and your data requirements. But if, as Adrian mentioned, you're looking to cover significant areas and generate incredibly high resolution to the point where you're getting 100 plus points per square meter, then yes, is the bottom line. But a cost comparison, a standard survey team in the field can go anywhere from $5,000 a day, and they're collecting individual survey points with traditional sightline equipment. So for a site, that's somewhat sizable, that could take a week plus. You can collect the same amount of data in a 20 to 25-minute flight.
Thanks. Are there other questions we can take? You can type your questions, or if you want, go ahead and unmute yourself and ask your question directly.
I'm sorry, I don't know if you can hear me.
Yeah.
Okay, because I'm not sure with my headphones when they work, when they don't. That's great work, and I'm so excited to see more information about this type of LiDAR. I've been using the one airborne, obviously not 100 meters per point, 100 points per meter, and that my question about that was. I'm assuming you can set, let's say, the amount of points that you want to capture, because for some applications, 100 points per meter, it's sufficient. And there will be cases, let's say, that that's an overkill. Is that something that you guys can do? And
yes, yeah. So to answer your question, UAV LiDAR is constructed in a way, is manufactured in a way that it's very easy to operate, so that you can mount it on a UAV, go scan the area, collect the data. Where we could limit the point density is after in post-processing, because we can filter out those points, and I'm always in the kind of mindset where you want to have more than less. So we were collecting, that data set was 320,000 points fired every second by the laser. So if we needed to decimate that data set, we could do it after in the software, in the processing software.
And would your data have information of the first, second return?
Yes, yes, it has multiple.
So that would be included in your last file.
Yes, yeah, exactly. That and the intensity as well.
No, it's really great to see. I mean, the high density and kind of following up what Alyssa asked, cost versus the area, because what would be, let's say, I guess, would you have a limit in terms of the area that you're able to do? Because obviously, like, 1 hectare, 2 hectares, or how that works. I'm just curious in terms of drones.
So I'll just, maybe Jamie will fill in the gaps, but usually the cost depends. There's a few factors that contribute to the cost. Is the area, the size of the area that's being collected, and as well what deliverables need to be pulled out from the data.
Okay.
So as we go further and further into the analyzing the data and identifying, classifying different features, the price certainly goes up, because that involves more time and work.
Yeah. So it's there is some like a basic post processing, let's giving a last and say you guys go ahead and play with the last file, and if you don't want to do more, then that's optional as well.
Exactly.
Yeah. Okay. No, that's great. Thank you so much for showing this. I'm doing some carbon work, so it's I have a student working with LiDAR, but not at this resolution, by no means.
Fascinating. Another thing just to mention too, I mean, obviously with drones, there are absolute limitations, both from a performance standpoint and from a regulatory standpoint. In Canada, at least at the moment, you're only allowed to fly within line of sight. So there are certain constraints to an operation if you're looking to cover significant areas of land. Acknowledging the fact that you need to maintain the drone in line of sight. So for this data set, for instance, how we coordinated it, Adrian and I both had direct communications. Adrian was the visual observer. I was the operator. He was standing on the south side of the building and I was operating from the north side of the building. And so we had visual line of sight from both vantage points, but hypothetically speaking, if I was about to lose visual line of sight, I would radio to Adrian, transferring visual line of sight to you. He would confirm, and that way the operation would still be within the regulatory framework. And then the other thing to consider is just the limitations of the drone that you're flying. Battery life being the main one. With the payload, the LiDAR payload that we had on there, we were able to fly, in optimal conditions with limited wind. Generally speaking, about 30 to 35 minutes per battery swap. And in that time frame, you're looking at covering anywhere from 60 to 80 hectares of land. So, it's pretty significant, but when you start to really expand to the point where you're looking at hundreds and hundreds of hectares in a single collect, you start to reach kind of the limitations of the technology as it stands now.
Maybe a bit related to that question. This is from Peter Reynolds. He says, can you talk about line of sight requirements with large survey areas, particularly say in forestry where line of sight is difficult?
Yeah, absolutely. It's a great question. And it really it depends on your area of operation. We always try and do a pre-scout prior to collecting data to find the height of land. And even if it is, outside of the specific area that we're looking to collect, if it's going to give us a better vantage point to operate from, we'll always either set up there or place a visual observer there to maintain visual line of sight throughout. Otherwise, you're basically having to kind of configure your operation, and this is what I was mentioning earlier about the importance of mission planning before you even get to the field. Is these are all things that you need to think about strategically to basically optimize your time in the field. So acknowledging the fact that visual line of sight is a requirement, you're either going to need X number of visual observers to maintain constant visual line of sight, or multiple takeoff and landing locations. As the case may be. It's worth noting too, the regulations are moving in the direction where they will start to encompass beyond visual line of sight operations. You can apply for, what's called a special flight operator certificate for beyond visual line of sight flights currently, but typically that's limited to Class G uncontrolled airspace. So any kind of urban application for the most part is out. And that's a whole nother set of hoops that you need to jump through. So I would say for the time being, just trying to optimize your mission planning is your best strategy.
I'll add to that. We were actually in South America doing a survey of a forest, and how we planned it out in South America was that as Jamie mentioned, we found the highest point in the area. And what we did is we did 2 surveys, basically combining them after on each side of the highest point, so that we could see down the hill from the area where we were operating, which worked out very well for us doing that survey.
Peter Reynolds had a follow-up question. He said, in the sample video, did that require an SFOC?
No, it did not, because we had, it wasn't controlled airspace. So we had obtained airspace approvals from NAV Canada. There's now a designated portal where you can apply as a drone operator for airspace clearance for a specific time window. And, because we were maintaining visual line of sight throughout the entire operation, an SFOC was not required. Of course.
Any other questions, either through the chat or just if anyone wants to unmute themselves?
Well, all good. As I said, we'll be sharing the data set. So you'll have time to, to play around with it on your own. And if subsequent questions do arise, again, please don't hesitate to reach out. We'd be happy to help in any capacity on that front.
Jamie, I'm not actually sure if people have your contact information. What's the best way for them to be in touch?
Sure. Yeah, I'll post my email in the chat right now. And contact information should also be available in the description of the YouTube video once it's posted live.
Excellent. Excellent. Well, thank you very much. That was super interesting and informative, and so relevant, particularly to the design disciplines and to forestry in our faculty. So I'm sure this will only be becoming more common as we move along. So thanks so much, Jamie and Adrian, and for everyone that was able to join us today. And again, if anyone has any questions, you can follow up on the YouTube or through Jamie's contact right here. So thanks very much. Have a great day.
Thank you very much for your time.
Have a great day. Thanks for everyone for tuning in.